So children, today in this video I will be trying to cover units of rate constant. Next, kinetics of first order reaction, kinetics of zero order reaction, and half-life period expression. So first of all, unit of rate constant. Suppose we have a reaction A2 products, and suppose the rate law expression for this reaction is R is equal to rate constant, concentration of A to the power n. That means this reaction is suppose a reaction of nth order, because power of A is n, so it's an nth order reaction. So we are trying to find the unit of rate constant. So you see from here we can write on rearranging, K will be equal to R by third bracket. So if I put the unit of R, which is moles per liter per second, unit of R, and the unit of A is moles per liter, concentration to the power n, and if we simplify this, it will be moles per liter to the power, here the power is 1 and here the power is n, so it is 1 minus n, and second inverse. So this is what we are getting, unit as unit of K. Now suppose first order reaction. For first order reaction, we have to put the value of n equal to 1. So 1 minus 1, will be 0. Anything to the power 0 is 1. So in that case, the unit will be second inverse. So this is the unit of K, for first order reaction. Let us find out in case of zero order reaction. Zero order reaction. So n value is 0. So it will be moles per liter. Moles per liter per second. It is the unit of K for zero order reaction. So in this way, by putting n equal to 2, you can get the order for, the unit of K for second order reaction. Okay, now before we go to the second point, let me give a question here. Question is, say, for the reaction A2 products, the rate of reaction becomes 27 times. The rate of reaction becomes 27 times on making the concentration of A 3 times. For the reaction A2 product, the rate of reaction becomes 27 times on making the concentration of A 3 times. So what is the order of the reaction? What is the order of the reaction? Now suppose we consider the order to be say nth order. So if it is nth order, then R will be A to the power n. Okay, now since it is said that concentration of A is becoming 3 times, so you see 3. So concentration of A is becoming 3 times, so that's why 3 Now 3 to the power what? 3 to the power what will become 27. And we know 3 to the power 3 is 27. Okay, 3 to the power 3 is 27. So the order of this reaction will be a third order reaction. Answer will be, this is a third order reaction. Another question of this type. Another question of this type. Suppose it is said for the reaction say 2A plus 5B arrow products. For the reaction, rate of expression is R is equal to K concentration of A to the power 2. Suppose this is the rate of expression. So the question is, what happens to the rate of reaction when concentration of A is say doubled, concentration of A is doubled, and concentration of B is made half. So for the reaction, this rate of expression given, what happens to the rate of reaction if concentration of A is doubled and concentration of B is halved? So you see, if it is double, 2 square is 4, and concentration of B is made half, so half. So on simplifying it becomes 2. So we are getting 2. That means rate of the reaction will be double. So answer is double. Rate of the reaction will become 2 times. So you should be prepared to answer like this type of question. Now we are doing the second point. We will try to get an expression for the kinetics of first order reaction. So suppose in general a reaction A two products, and suppose it is a first order reaction. So if it is a first order reaction, our rate will be K A to the power 1. This is an expression for rate of first order reaction. Now this rate we can write as your decrease rate of disappearance of A, which is we can write minus dA by dt. Rate of reaction is equal to rate of disappearance of A, which is equal to say Ka. So this follows, and on simplifying this we can get suppose this minus we take it this side, it will be minus K dt. So this is what we get. Now we will be doing integration on both sides. On integrating both sides, we get is equal to minus k dt. Since k is a constant, it will come out of integration. Now this is standard form of integration. This the integration of this thing, this is standard form. Let me write down is integration of 1 by x dx. Of this form it is integration of 1 by x dx. It is log x plus c. Log x plus c. So here, in science we take natural log. So here it will be ln a and a constant will be there, a constant of integration that we will write on one side, because here also we will get constant of integration. So it will be minus k. The integration of dt is this standard form. Integration of dx, it is x plus c. This is standard form. This is another standard form. So x plus c, and of this one, it will be integration of dt is t plus your integration constant. Suppose I naught is the integration constant. Now we have to find out the value of this constant. So to find integration constant, what we do, we take up initial condition at t equal to 0 at initial time. Suppose the concentration of A is A naught at t equal to 0. That is, initial concentration of A is A naught. So putting this condition here, we will get ln A naught is equal to minus k into t value 0 plus I naught. So what we get from here is ln A naught is equal to I naught. So this is the value of integration constant. Okay, so we can put this value here to proceed further. So we have ln A is equal to minus k t plus ln A naught. Okay, now if we write like this, if I take this on this side, from here we can write ln A naught minus ln A. So it will be our A. This on rearranging, it will become like this. So from here ln this is minus, the rule ln this, it will be A naught by A. Is equal to kt. Now to convert natural log to common log, we have to multiply. We multiply by a factor of 2.303. So on multiplying this by a factor of 2.303, we have 2.303 log A naught by A is equal to KT. Or log A naught by A is equal to K by 2.303 T. So you need to remember this form of the equation, which is equation for first order reaction. This may be useful in solving numericals on first order kinetics, first order reaction. Okay, now one more form we have which is very common in case of first order reaction. Suppose an initial concentration, we take it as A. The initial concentration we have taken as A naught. Suppose let us also represent it by small a, and at time t equal to 0 there won't be any product. Now at time t equal to t, suppose x amount of this reacts. So if x amount reacts, so A minus x will be left behind. So this is the concentration of A, or amount of A, small a, at t equal to 0, and amount of A is A minus x at t equal to t. So putting these values here, we will have log of A naught initial concentration is A by, at time t it is A minus x is equal to A by 2.303. This is another form of first order kinetics that we need to remember. So what we have here is x is the amount reacted, E is the initial amount of reactant, K is the rate constant, T is the time. So now let us talk about half-life period. Half-life period, which is represented by T half. What is half-life period? It is the time for half completion of the reaction. Time for half completion of the reaction is called half-life period. Suppose a reaction is completed in say 60 minutes time. So its half-life period will be 30 minutes. Suppose a reaction gets completed in 150 minutes. Then its half-life period will be 75 minutes. Okay, so let us find out expression for T half. So we can start with this. Say log A by A minus x is equal to K 2.303 into T. Log of I think it will be better if I start from this one. Let's start with this one. So this we have, and now applying half-life period. Suppose T half. We know at in half-life period, half of the amount of reactant disappears and half will be left behind. Half will react and half will remain. So concentration of A at time t, or at time t half will be half of this. Will be half of this. That is A naught by 2 has reacted and A naught by 2 is left behind. So on simplifying this, A naught will cancel and we get log 2 is equal to A by 2.303 T half. Okay, now the value of log 2 is 0.3010 A by 2.303 T half, and we can write T half value will be 0.3010 multiplied by 2.303 is multiplied, now we get 0.693 by A. So this is the expression for half-life period in case of first order reaction. Now children, in this way you have to do for zero order reaction also. Okay, now I am just giving you a hint for zero order reaction that you should try yourself. Okay. So if we consider this reaction, suppose if this reaction is a zero order reaction, then we will get R rate will be minus dA by dt is equal to K A to the power 0. So this is what we will get, and it will be 1, so minus dA by dt is equal to K. So that is minus dA is equal to K dt. So this is what we get, and on integrating this, we will get integration of dA is equal to minus K dt. So I do integration on both sides, and integration of this will be this, and integration of this will be T and plus constant of integration. So to find the value of I naught, if we put the initial condition at T equal to 0, concentration of A was A naught. Putting this, we have concentration of A is A naught minus K into 0 plus I naught. So this is the value of I naught we get, and so if we rewrite this one, we get A is equal to minus KT plus A naught. So this is one form of kinetics for zero order reaction, and if I write it again in another form, it will be A naught minus A. If I take it this way, it will be K. So this is also one form. This is also another form of kinetics for first zero order reaction, and if we represent the initial concentration by A, and X is the amount reacted, so it will be A, and here it will be A minus X. A minus A minus X, it will become X. So X is equal to KT. Okay, it is also another form of kinetics of zero order reaction. Now coming to the half-life period expression in case of zero order reaction. Now we can let us start from here. So for A naught, we write A naught only, and concentration at time t. At time t will become a half of this. Because half has reacted, half will be left behind. So is equal to, and here this is K into T half. So this for half-life period will become like this, and on simplifying this becomes A naught by 2 is equal to K into T half. So the final form of half-life period expression in case of zero order reaction, this one on simplifying will become T half is equal to, this K will come in the denominator, so it will be A naught by 2K. So this is the expression for half-life period in case of zero order reaction. This was the expression for half-life period in case of first order reaction. So if you see that, if you compare, you see here in case of zero order reaction, it depends on the initial concentration, whereas in case of first order reaction, it is independent of initial concentration. So in this video, we have covered all the topics that we are supposed to do. So this much for now. Thank you for listening, and bye bye.